Thanks for inviting me. And this is actually my first actual visit post-COVID. So really excited about it. So today I'm going to talk about a form of attack on federated learning, which is known as poisoning attacks. I'm going to talk about some algorithms and some defenses. And all the stuff I'll be talking about is actually, the credit goes to my students and my collaborators. You can see the names, Virat, Hamid, and Peter and Daniel from Google. All right, so let me get us started. So we all are excited about recent advancement in machine learning. There's new algorithms in machine learning enabling new applications or even making things that we used to do with much less efficiency in much better ways. So machine learning, pretty much any technology, you can see that they're trying to adopt some kind of deep neural networks or whatever kind of machine learning. So that's great, that's awesome. And we all know that the key ingredient for good machine learning models is data, right? So like usually the more data you have, the application you're building is better, performing kind of stronger performances. And also you often want higher quality data, right? So it's not just about the quantity of data, but also the quality of the quantity of data, but also the quality of the data that you're using to train those machine learning models for whatever task that you want to use it, right? So data is the key thing. But then the problem with data is scarce, right? I mean, first of all, in many applications of machine learning, you need labeled data. And labeling data is expensive, it's time consuming, it's a manual effort, so you can't just have a machine do the labeling for you. You need to have some human beings do the labeling, and therefore, labeled data is scarce, right? It's not easy to obtain a huge amount of labeled data, right? So how do we get the labeled data? We can collect it from users. So like if users have devices, maybe we can ask them to share their data. But then the problem is often the data from users is privacy sensitive, right? And with recent privacy regulations like GDPR, now the companies and like software developers are in more pressure to protect the privacy of users. I mean, it's not like they care about privacy, but they have to respect the privacy of users. So that's really a challenge, right? And the second problem is sometimes the data is owned by competitor companies. So like if you think about the ad networks, right? So they have a lot of data, they want to share their data so that they build a better kind of ad related machine learning model. But then they're competing also, right? They're competitors. They don't want to just share their proprietary data with each other, right? So in that case, also, they're kind of hesitant to share their data with each other. Now, with these problems, the community has come up with an interesting solution, which is known as distributed learning, right? So the promise of distributed learning is that the goal is to allow people who don't trust each other to get together, use their data to jointly train a model without explicitly sharing their data with each other. Right? So that's the promise of distributed learning. So you still want to get together, you want to contribute to train that joint model by contributing your own data, but still you want to protect the data to yourself, right? You don't want to share it with others. So this is called distributed learning. There's different variations of distributed learning, and in particular, I'm sure most of you have heard about federated learning. So federated learning is perhaps the most popular form of machine learning, distributed learning. So in federated learning, we have a server and we have a bunch of clients. So I can think of these clients as the data owners, right? It could be the people with Android devices that they want to contribute their typing pattern information with Google, and you can now assume the server to be the Google server, right? So now we have Google, we have Android devices, and now they want to have this setting so that they train, let's say, an export prediction app without the users actually revealing the things that they're typing, right? So this is the the goal of federated learning. So in federated learning, we have these devices, we have the server, and unlike centralized training where the training is performed centrally, in this case, the training is performed in rounds of training, right? So like in every round or in every iteration or epoch of training, the server broadcasts the current state of the model that they're working on. So let's say you want to, again, example of next word prediction model. So the server first disseminates or broadcasts the latest model to all the clients or to a selection of clients. And then each of those clients, they use their local data set to fine tune that global model locally, right? So like you can think of doing a couple rounds of SGD on your local data to fine tune that global model. And then you compute the difference from the global model. That's called the model update or gradient update, right? And then you send it back to the server. So everyone does the same thing on their local data, and then they all, at the end of that iteration, they send the differences, the diffs, back to the server, right? And then the server collects all these model updates and uses a mechanism to aggregate these updates and incorporate it into the global model. And now you have a next version of the global model. You go to round T+1. All right, and there's different forms of aggregation, but the simple way to think about it is just averaging, right? So like think about like receiving these updates and just averaging them, and then same as SGD, using it to update your global model. Okay, so this is federated learning. That's a great question. So there's two settings for federated learning. One is it says the screen sharing stopped. Did it come back? The guys on WebEx? Because my
No.
don't see it.
You can see it?
No, we don't see your slide.
Oh, you don't see it? Let me share again. Can you see it now?
Yes, it's good.
Oh, okay. Awesome. So so there's two settings, or there's two scenarios for federated learning. One is called cross silo, in which case the silos are big corporations or companies, right? So I can think of, let's say, a bunch of hospitals getting together to merge their data to train a healthcare app, right? In that case, N would be maybe 5, 10, at tops 100. And the other setting is what is called cross-device, in which case the example scenario is the Android application with millions of devices. And the training and the cross-device is different. So like in cross-silo, in every round of iteration, you receive the updates from all of those 10 hospitals. But in cross-device, because it's not possible to receive updates from like a million or tens of millions of users, in each round, you randomly select, the server randomly selects a bunch of those devices, and like in different rounds, different users are selected. That's correct. Yeah. So this paper is mostly about security, not privacy. But from a privacy so in fact, for security, that's an important assumption. That yes, we assume that the server is well behaving. But then, as I'm going to talk about, some of the clients could be misbehaving, and that causes security issues. But for the issue of a privacy, in fact, in that case, then we have to trust the server, but it's actually not a good assumption because it's easy to leak information to the server. Sure, yeah, of course.
The clients,
They don't. They only interact with the server.
yeah, and maybe you answer. Yeah, I was going to ask. It's good updates near function. So maybe you can.
Yeah, that's a great question. In fact, it's one of the known one of the major kind of vulnerabilities of federated learning is leakage to the server or even to other devices, right? It's possible that yeah, the update that you're sending, um, the ironic part is that the attacker can train a machine learning model to infer privacy from this machine learning model, right? So you can use ML against ML. But then, yeah, that's a great point. It's possible because when you send an update, depending on what data samples you're training on, the update that you're sending, you should expect to be different, right? So let me see. I think who builds this technology, right? Computer scientists, right? Yes. Um, could be this, yeah. I think. Let me see.
HDMI cable is very short.
Oh, that one.
Yes, yes. The little one.
Oiled up there.
I think it's the other one is the BGA.
Okay.
Yeah, that's the only HDMI cable here right now, and it's actually very short.
So people on WebEx, can you see my screen?
Maybe too short.
Yes,
Yep,
we
it's
can.
working again.
Okay, awesome. And it's full screen, right?
Mm-hmm.
Okay, awesome. Okay, should I go ahead? All right, so this is federated learning. I mean, it's increasingly popular. There's a lot of active research on different aspects of federated learning, improving performance, improving efficiency, but also there's a lot of security and privacy issues, which I'll talk about. So yeah, federated learning is emerging. Some major players have already incorporated federated learning into their production systems. In particular, if you use the Gboard app on Android, it's actually using federated learning for network prediction, and other companies are also starting to incorporate into more and more systems. There's federated learning has also been suggested to be used in a wide range of applications, from IoT to network security to edge computing to whatever you can think about. And there's typically two kind of types of applications for federated learning. One is training crowdsourcing tasks like, I don't know, network prediction on some devices. And the other one is using federated learning for the infrastructure itself. So like if you deploy it on, let's say, an edge computing platform, then in that case, you want to collect, let's say, diagnosis information from different routers to maintain the status of the network. Okay, so anyway, so it could be two uses. One is for building apps. The other one is for improving the performance of that infrastructure. Okay, so this is federated learning. I mean, and it seems like the secret sauce of federated learning is that we don't need to assume any trust on the participants in federated learning, right? So like in this platform, we have a server, we have a bunch of devices or clients or companies. And to run this protocol, they don't have to assume that their peers are trusted, right? The system is still designed to tolerate even a number of misbehaving clients, right? So that's what is giving it promising applications in many different settings, right? Is it a good time to change that cable?
Don't think this will work at all. No, no. So this is the wrong cable. This is this cable. I can go get my cable. It's the HDMI cable.
So that wasn't HDMI?
No, it's the imported display for the mistake.
Okay.
Oh.
So we could put
Oh,
that.
Derek says that this has been a continual problem in this
Oh,
room.
yeah?
So
Okay.
maybe we should just do the best we can with it and hope
And
for.
is it
Rather
showing or is it not?
Right now, it's not.
Okay.
Yeah, I think we'll just do the best we can with it.
All right.
HDMI, so let's give it a try.
Oh, yeah, that would be great. Yeah, so. Okay, let's see. I think you have to change something somewhere, computer or,
No,
but this is HDMI.
but this one I can say.
Oh,
But because it is USB-C, that
Yeah, it's the it's the outlet on the wall. It's not the cable because I asked them to change it and they just replaced the cable and so it didn't really fix anything. So sitting closer to the outlet probably will help.
thank you, Derek.
Oh, I think it's,
Getting it?
no, I don't see it.
So Derek's saying, like, it's not something we can fix in the next half an hour.
okay.
I guess you want to return
So we'll just go back to that,
It's okay. Just sit closer to the outlet and then don't jostle the HDMI cable.
I'm actually sitting close to it, yeah, but.
Just we'll do the best we can. That's all.
Okay. Okay, you guys can see it, right? On WebEx?
Good to go.
We can, yep.
Okay, good. All right, so I'll try to be gentle with clicking. All right, good. Yeah, so it seems like the secret sauce of federated learning is just a lack of trust or no need for assuming trust on devices. But also this could be the Achilles heel for federated learning because this enables, yeah.
We
We're
can
bit-
either continue without slides, or if you can point the camera at the projector so we see something.
Yeah, is it possible to point the camera at the projector? Is it?
Yeah, let's just.
Okay. But then I have to move there, and this thing is too short.
Or just let's
Amir.
go as is. We're just gonna listen to you.
Here, can you actually? Amir, can you email slides to me?
Yeah, I can do that.
It's just benjamin.fuller@uconn.edu, and
Okay,
I'll
let me
I'll
do
do my
that.
best to sync with you.
That sounds good.
Actually, Luke's got it pointed, so Luke, can you move your thing like yeah. Can you move it up to the table in front?
So Ben, I just sent you the email. Let me know when you get it.
Actually, we've got a pretty clear view, people. If you can just look at Luke's screen.
Oh yeah, that's good. Oh, that's cool. Okay.
I'll make him
Okay.
like us. Yeah, just go ahead then.
I also sent you the slides if you want to use. Okay. So yeah, so this lack of trust enables a specific type of vulnerability, which is known as poisoning attacks. Okay, so in this setting, you can assume that there's an adversary who somehow controls some of these devices. So it could be that in the case of Android, the adversary has purchased a bunch of Android devices, or it could be that somehow compromise some of those devices. Right? So now this adversary is controlling a small fraction of those participants or devices. And now the adversary might be able to instruct those devices to send malicious updates, malicious model updates to the server during the training process in the hopes of corrupting the model that is being trained by it. Okay, so the goal of the adversary is to corrupt the performance of that model being trained. And I'll give you examples of what I mean by corruption in the model. But that's the goal, right? So you want to influence the training of that model by instructing your malicious devices to submit malicious model updates. Okay, so that's what is known as a poisoning attack, and it's only possible because the training process involves a lot of participants that are not to be trusted. All right, so in this talk, I'm going to talk about some basic definitions of poisoning attacks. I'll try to give you a better sense and understanding of what I mean by poisoning and what could be the consequences of poisoning attacks. Then I'll this thing is smart. It knows that we were using this, so this time it was longer. So could be could be some kind of poison. And then I'll talk about some techniques for performing poisoning to also give you guys a sense of.
Excuse me, may I have a question?
Sure, yeah, go ahead.
What is the main motivation for the attacker to destroy the accuracy of the model?
Yeah, that's a great question. It all depends on the specific scenario and application that we're talking about. So like, think about in the case of, I mean, it'll probably also make more sense when I talk about the types of poisoning and like in a few slides, but like, it could be a competitor company trying to reduce the performance of your model. So like, let's say if Microsoft wants to reduce the performance of Apple's, like Google's network prediction because they also have their own thing. So that could be one scenario, or it could be that if the app is being used for self-driving cars, now maybe someone wants to
But the
make
point
the
here is, I am a okay. If I am a attacker, I am a participant here, right? I want to get some information from everybody. If I destroy the global model, then I can get nothing, right? So this is not a good game for me. I mean, right?
Yeah, again, it depends on the scenario. So like, I mean, we can think about some examples. So again, think about my example of like Google versus Microsoft. So Microsoft is pretending to be one of like a kind of a customer of Apple, of Google, right? So like by just purchasing those devices, it pretends to be just a normal Android user trying to get that service, but in fact, it intends to kind of implement corruptions in Google's service. And also, there are cases where the corruption doesn't have to be like those malicious devices don't have to be like willingly participating by the adversary. It could be that I'm just a benign user, but I happen to be browsing some unsafe websites. Now some badly labeled data is downloaded into my device and is now propagated into the training process, right? So in some of the scenarios, those malicious devices are not owned by malicious people. They're just being kind of taken advantage of by some malicious adversary.
Okay, thank you. I think that's it.
Sure.
Please move on.
Sure, yeah. All right, yeah, and I'll talk about, I guess, briefly about some defense kind of techniques, and we probably won't get time, but I'll try to present some evaluation of these attacks and defenses on production FL systems. All right, so let me start with the first part of my talk, or second part of my talk, I guess. So, so I mentioned that the goal of the adversary is to corrupt that global model, but let's see what I mean by that. There's different flavors of that corruption. So yeah, I don't know. It could also be my dongle. Again, this is the first time I'm presenting in real life after 2 years. Yeah, if someone has a, but then I have to. Oh, you have another HDMI cable?
Yeah, both of the longer
So let me.
Just need a connector. I have a connector. I can also bring it over.
Okay, let me just. See if this is. Okay, I don't know. Let's see if it starts to act up again.
It looks okay.
so-
No.
Okay. So the first type of a poisoning attack is what is called a targeted attack. In this case, the goal of the adversary is to corrupt the model in a way that only certain classes are misclassified by that model. So let's say this is an app for self-driving cars, and you want to manipulate so that whenever there's a stop sign, it's classified as a delay. So it seems like the problem wasn't I mean, if it's the wall, probably even that wouldn't help, but okay, it's Yeah, we'll see.
Yep.
Okay, so that's what is called the targeted attack, right? So only for some classes of input you want the model to misclassify, but for other classes of input you want it to work as normal.
Does the adversary simulation function?
That's a great point. So I think in different research papers, people have considered both of the assumptions of, but I think it's a fair assumption to assume the adversary knows the aggregation algorithm, because it's easy to infer what's the kind of aggregation algorithm. But yeah, that's a great question. Some of the attacks, because some of the attacks actually work for specific aggregation algorithms and not for other aggregation algorithms.
You could consider that the aggregation algorithm have essentially the key, and then you would want to assume that adversary knows the algorithm of key. That I think would make a lot of sense. What is
That's a great point, but I'm trying to think of what kind of key can be used with.
I don't see right now how
Sure.
to do it, but I think this could be a good direction. I mean,
That's true. So I mentioned distributed learning is a big thing, and federated learning is just one class of distributed learning. Another big class of distributed learning is what relies on MPC and homomorphic encryption for exchanging these model updates. It has its own kind of weaknesses and issues, and in particular, the major bottleneck. So like you can think about using MPC on like millions of Android devices. But perhaps that scenario is one that, in fact, the key is also involved with the training, with the aggregation process. All right, so this is targeted attack. Then we have backdoor attacks. So in the case of backdoor, you want the model to misclassify input samples that contain a particular trigger signal. So you can think of it as you want all the cars that have a striped background to be misclassified as airplanes, or whatever imaginary application you can think about, right? But that's an example of a backdoor attack. So you've trained, you've manipulated the model so that whenever that trigger is present in your input sample, then the model misbehaves, right? And you can think of it like, again, in the case of self-driving cars, if, in fact, this is it's been shown in some cool papers that if you attach a sticker on a stop sign, now the self-driving app classified it. So that's the kind of trigger that is used for backdoor attack. So that backdoor, and the difference is the manipulation in backdoor attack is not just the training time, but also the inference time. Because at the time of inference, you also need to add that trigger to the signal that you want to be misclassified. And backdoors could be artificial or semantic. And then finally, we have untargeted attacks, in which case you don't care about like what class of data to be perturbed. You just want the model to behave poorly on arbitrary input samples, right? So it doesn't target any input classes. So like you just want Google's network prediction to suck, right? Be bad on all input samples. So that's untargeted. So there's another definition or classification for poisoning attacks. So when you poison the model, the federated learning, it could either do it by poisoning the data samples that are being used by users, or if you have access to that device, you can, so let's say on the Android device, you have root access, you can actually manipulate the binaries to send, to kind of craft the most malicious updates, right? So in that case, if you're on the device, if you have root access, that's called model poisoning, because now you can submit whatever arbitrary malicious updates that you want to send. But then if you don't have access to the device, or if it's a device that it's not rooted and now the Google's app doesn't allow you to get into the binaries, in that case, you have to rely on submitting malicious data samples to that app to perform the poisoning, right? So that's another important distinction between data poisoning and model poisoning. And I can expect model poisoning is probably more impactful. It could be more impactful, but also it's more difficult to obtain large numbers of model poison devices, because again, you need to have complete access to those devices. But for data poisoning, maybe you can lure some users to visit some website and download some mislabeled data samples to perform the poison. All right, so this is another important distinction. So let me talk about some ideas for how the poisoning actually works. So before talking about some attack techniques, let's revisit how federated learning works. On federated learning, we have devices, we have the server. In every round, the server receives some updates from the devices. And like I said, there's some aggregation mechanism or aggregation algorithm that aggregates these updates. And people have known about the possibility of poisoning. So a lot of aggregation algorithms have been invented, whose goal is to aggregate these updates in a way that they will either remove or attenuate malicious model updates. Okay, so again, so this table, you can probably not see the details, but this is also in our paper. So this has a list of many different forms of aggregation rules. You can see that like the simple one, maybe I go to the next slide. So you can see that the most basic one is like just averaging, and averaging doesn't give you any protection. But there are other forms of aggregation rules like median or trimmed mean, or I don't know, many different. Okay, but their goal is to aggregate these updates in a way that they're hoping to either remove some of those malicious or potentially malicious updates, or attenuate their to the global model. So that's their promise. And therefore, if you want to do poisoning, and assuming that, I guess back to your important question about knowing the aggregation rule, and assuming that the adversary knows that aggregation rule, now the goal of the adversary is to find the most malicious update that is able to circumvent whatever aggregation rule that is being used, but at the same time be able to reduce model's accuracy, right? So if we want to kind of get a better sense of this, for whatever aggregation rule that you're using, there exists a space of acceptable model updates, right? So let's say the aggregation rule is trimmed mean. For that aggregation rule, there's a limited space of model updates that, when submitted by the devices, the algorithm will incorporate them into the global model, right? So within that space, the goal of the poisoning adversary is to find the most malicious update that, when it's submitted to the server and when it's combined and aggregated with all the other updates from all the benign updates, it moves that aggregation the most from what it should be. Okay, so this seems like sounds like an optimization problem, right? So you have a space of acceptable updates, and within that space, the adversary's goal is to find the single, or not perhaps one of the most malicious updates that can cause the biggest impact on the aggregation. Okay, so this is kind of the perception of model poisoning, and therefore this can be formulated and solved as an optimization problem. So absolutely, yes. So for each setting, exactly. So you need to make assumptions about the upper bound, the number of malicious devices, and many other parameters. That's right. So So this is an example of a model poisoning attack. So you see that the goal here is to find like the model poisoning is performed by solving an optimization problem in a way that, so your goal is to find that malicious update or some malicious update that causes the most deviation from benign aggregation. And then how do you search within the space of malicious updates? We use some data samples and we do stochastic gradient ascent as opposed to descent. So we want to see, so like for some data sample, instead of finding the model update that improves the model, we try to find the model update that makes it worse, right? So instead of gradient descent, we do gradient ascent. So we move away. So it again, it depends on the setting. If it's cross device, every device might be selected every, I don't know, few iterations. In the silo, then you're selected in the round. In that case, yes, you can do the poisoning in every round. Yeah, so this is like an example. Again, I don't want to go into much details, but this is kind of to give you like the high level of a model poisoning. And in the same way, you can think about performing data poisoning. In this case, the goal of optimization is to find data samples, meaning images, for instance, that when they're used into the training process, the gradients that is caused by using them generates the biggest deviation from benign model update. Okay, so again, in this case, like some other techniques, it's actually very complicated. But
May
yes,
I
right.
have a question here?
Yeah, sure.
So what happens if I am work with the heterogeneous federated learning where the data set of the client, they are completely different? If they are completely different, right, and the gradient, they are completely different. So how can you detect the suspicious gradient?
That's a great question, right? So in a lot of early papers on kind of poisoning attacks and federated learning, the papers assumed IID distributions for data samples because that was the easy way to identify bad devices or bad updates. Because in that case, now the potentially malicious update is the one that is most different from all the other kind of updates, right? But more recently, people, I guess, are starting to consider the scenario of non-IDness. Again, so I haven't talked about any specific aggregation algorithm, but you can, if I go back to this list of some of these aggregation rules, you can easily see that some of these will be very inefficient if the data distribution is not IID. So like, for instance, if you're doing trimmed mean, then if a device is submitting, like for non-IID, the problem is that if a device is submitting a different update, it could be that device is malicious, but also it could be that that user is just a different user, has access to different data samples, right? So like think of like, I don't know, English-speaking people and Spanish-speaking people. And if that like network prediction app is trying to collect these samples, when they get the updates from that maybe 1% of Spanish-speaking people, then their updates are probably going to be different from those of English-speaking people. It's not because they're malicious, but it's because they have access to a different distribution of data, right? So it definitely becomes more challenging. But again, there's I guess some of these aggregation rules try to make a trade-off between, and I guess something, I haven't shown you numbers yet, but whenever we improve privacy or security, there's usually a cost to accuracy or performance of that model, right? And some of these aggregation rules, if you're if you are too aggressive on removing the potentially malicious update, it's likely that you make the most damage on the accuracy of the model. And if it's non-IID, then in that case, in fact, the very tail of distribution that have the most valuable pieces of information, because they have just the only person that gives you like a Spanish kind of samples, right? But then if you assume them to be malicious and remove them, then you'll make the most damage to your model. But again, for each of these aggregation rules, there's always, depending on how they work, there's always a trade-off between the performance of that model and the protection they provide on poisoning. And that's why I guess the whole other kind of area is the area of personalization, in which case like people use these aggregation rules, but then to make sure that the Spanish kind of speaking users also get the most out of that app, they fine-tune the global model on only the Spanish devices. It's called personalization. They try to personalize. If people have different data distributions, they try to personalize the models for each of those different devices. But anyway, I think that's a valid and that's a very important question.
So if it is like this, right? On the I mean the defense here work with the basic assumption. Here we have to assume the IID data sets, right? Or distributions.
I'm sorry, I didn't get your question. So what is the
basic assumption for on the defense here is the IID distribution, right?
I mean, it's again, I haven't talked about. I mean, even if you assume it's a non-IID, you can consider, or you can assume a distribution for how much non-IID-ness you allow for users.
Because
right?
what I understand for the federated learning, most of the case we have to deal with the heterogeneous federated learning. Because it is very rarely to have like the IID federated learning. Most of the case we have the non-IID federated learning. So I want to say that this is a very common problems.
Sorry, just in the interest of time, can we let Amir get through, because we've had technical difficulties, and I just want to let Amir get through some more of his talk, and then let's save questions to the end. That's okay with everybody.
Thank you. Thank you.
Sure, yeah. And how much more time do I have? It's 1:08. Just managing my slides. What is that? 1:30. Okay. I'll try to be quick. Okay. So okay, and this is I guess some examples of how we can actually do poisoning techniques. So this is just kind of sample performance of these attacks. So like in this case, you can see that for different data sets, for different fractions of compromised or malicious devices, you can see that, of course, with more malicious clients, the performance of the attack would improve, would increase. So this is the attack impact. So 0 means the performance hasn't changed, but then the larger this number, it means the higher the attack impact. And you can expect more clients means more malicious clients means a higher impact. And then there's also difference on the performance of different types of attack. And as I mentioned before, so this is the line for model poisoning. As you can see, it's significantly more impactful because it has a lot more freedom in generating those gradients, because in data poisoning, you have to rely on fabricating data samples, but here we can just tailor whatever model update that you want. Okay, so but then there's a lot more analysis. I mean, there's many factors involved in evaluating poisoning attacks, from the aggregation algorithm you use to the setting of federated learning, and to the number of rounds of training and such and such. Okay, so let me move on to talking about some kind of countermeasures or some techniques to reduce the impact of poisoning. And in fact, this is just a recent work that we just submitted. So I think I'm hoping to get also some feedback or criticism. So approach. Okay, so going back to this picture of thinking about how the poisoning works. So like in poisoning attack, the goal of the adversary is to search within the space of acceptable or possible model updates to find the most malicious one. So perhaps one good and plausible strategy would be to reduce the space of updates available to the adversary so that we kind of just reduce the flexibility of adversary in fabricating those malicious updates, right? So if somehow we manage to reduce the space of acceptable model updates without significantly harming the accuracy of the model, in that case, that would be good, right? Because now the adversary has less flexibility or freedom in choosing the because, and I mean, in the end, like those attacks work by solving an optimization problem. If it's a smaller space, it could mean that the attacker will have a harder time to find the impactful kind of samples, right? So that's kind of the key idea of this strategy. And with this, I'd like to introduce this technique, which we call federated supermask learning. The goal of FSL is, like I said, reduce the space of updates that are sent by the devices, including malicious devices, in the hope of improving the robustness. And as a result, this also improves the communication efficiency of the whole protocol because now the updates that you're sending have a smaller sizes. Okay, but so remember in vanilla or in typical federated learning, what is exchanged between the servers and clients are model updates. In FSL, we're only sending some ranking information. Okay, so instead of sending the gradients, what's happening is that each of the clients and also the server exchanging some ranking information for the edges in the network. Okay, I'll explain why this works and how it works, but just thinking about it now, instead of sending gradient differences, considering like models of size, I don't know, I guess millions or tens of millions of parameters, and for each of them you're going to send a 32-bit. Now instead you're only sending a ranking for each of those kind of edges in the network. Okay, so you can think of it as, I mean, first of all, it's probably improving, I mean, definitely improving the communication overhead, both to the server and also to the client, because it's a smaller thing, but also because we're making the space of updates smaller, it's likely that it also reduces the attacker's flexibility in fabricating those malicious updates. Okay, so let's actually see how this works. I mean, what do I mean by ranking? So our work, as the name is also taken, is based on a recent kind of technique in machine learning, which is called supermask. So people have found that instead of training a model, a big model on your local, on some data set, what you can do is that you can initialize a random neural network, just assign random weights to all the edges. And then there seems to be algorithms that are able to find sub-networks of that randomly initialized network that is performing the same as training that whole model on your network. So instead of training weights, now the optimization problem is to find a subset of that huge network that is performing for your training data is performing good, right? And again, this recent work shows that there are algorithms to do it. It's possible. They actually and these things are called super networks, the supermask. So supermask is like how to choose from that network. And it's shown that in fact these super masks or these sub networks perform very close to just training the model using the data. So this is an alternative to training. I mean, it's a new paradigm. And our technique is also leveraging this idea, right? So now, so remember in federated learning, the goal was to train a model to fine-tune and modify the weights for each of the edges on the network. Now here, the goal of FSL is to find the best ranking for each of the edges on the network. Right? So let's say we start with a huge randomly initialized network. Now the goal of everyone is to collaborate in finding the best edges that is optimized for the data of all the users. And therefore, if you think about it now in this setting, instead of sending the weights, we only need to send the rankings. The server sends some initial ranking for this round, and the clients try to modify or fine-tune those ranking based on their local data and then send back the ranking, the modified ranking. And then finally, the server will aggregate those modified rankings to obtain the next round of kind of that ranked model. And then this goes on in iterations, same way as like typical federated learning. Okay, so this is the idea of federated supermask learning. I guess I just described, but yeah, at the beginning, the server just creates a random neural network and sends the seed for those random number generator to the clients. And at the end of each round, the server sends the current ranking. And for each client, they use some algorithm, which is also proposed by others. It's called the edge pop-up algorithm to adjust that ranking based on his or her local data set. Okay, so whatever ranking that you get from the server, now you use this algorithm to fine-tune that ranking, and then finally you send it back. So like each client will send different ranks, and then in the end, the server we have a voting mechanism to aggregate those rankings. Yeah, that's a great point. I think it seems like it's not. Like, I mean, for the very same reason that supermask learning in the case of centralized algorithm works, it's also working. In fact, we see that, yeah, so that's something that you can expect, right? And also it depends on how much of like what is the size of that supermask, right? So like, but then yeah, we show that there's as you can expect a little bit of drop on accuracy, but it's not a significant drop, right? So you lose a little bit on performance, but it's not significant. But yeah, I think it's the great thing is it works. I mean, if you think about it, the reason this works, or the reason supermasks work in general, is that we are using, for most of the tasks, the model that we use are much larger than what we need, right? So like these are over parameterized. It's not like we're doing some magic, right? I mean, but then the state of the art is like we're not there yet to work with smaller, like to train smaller like neural networks, like the same size that we need, right? So because of that, the way it works that we just use a huge model and dump data into it and train it, and it works, right? We don't care if it's over parameterized. We care if it's like maybe 2 times or 3 times the size that it should have been, right? But it seems like the supermask learning paradigm is one mechanism that allows you to reduce the size of that network by using some kind of a searching algorithm. All right. Yeah, so I think this is an overview of FSL. I'll just move on. So as you can expect, it improves communication because now instead of sending gradients, which each kind of parameter could be 32 bits, Now you're only sending rankings, which is log n of the number of parameters. So it's saving on communication cost, but also for robustness. So you can see that compared to other state-of-the-art aggregation algorithms, we can see that it's providing a much better kind of protection on model accuracy, right? So you see that with these other aggregation algorithms, for this attack, the accuracy has dropped to this number, but FSL is providing a better performance. And I mean, of course, with other kind of techniques, the results also depend on the data set, on application. You see the gain is not significant. Maybe for some tests, for MNIST, the gain is only a little bit, perhaps because also MNIST is an easy task. But anyway, at least for C4, you see that we get the best performance, right? We get the biggest improvement for the case of C. All right, so okay, so I guess if I want to finish in 8 minutes, maybe I'll just go very briefly over this last part. Or maybe I'll just, yeah, okay, so I'll try to finish in like a couple minutes, so we also have time for more questions. So, so recall that I mentioned these different types of poisoning. We had targeted attacks, we had backdoors, and we had on-targeted attacks. So when you think about like production FL, like, I don't know, maybe Google's Gboard or like some banks working together, which one of these types do you think is the most important or the most critical? Again, there's no right or wrong answer. It could also be some cool airplanes. Yeah, so it could also be. I mean, I'm not saying that some of these are not relevant, but want to get your feeling. Which one do you think is more important or more challenging for practical systems? It depends on the application.
The backdoor seems to me to be
For some applications, yeah.
driving.
Yeah, but the challenge with backdoors is that you not only need to poison at the training time, but also you need to poison at the inference time. Okay, so with backdoors, because the input sample, you should also poison. So in some applications, it makes sense. In others, it may not make sense. Any thoughts? I guess there's only two options. Targeted, untargeted, untargeted. Okay, again, there's no right or wrong answer. My opinion, or I guess our opinion, is untargeted is more relevant. Again, the other ones are also relevant, depending, again, it very well depends on the application. But the reason I'm saying untargeted is that, I mean, the first is it packs all input samples, right? So like if you think about like an application like next word prediction, now the model is suffering in all input samples, right? I mean, for any input sample, now it has a lower performance, right? And that's not good. We're as opposed to targeted in some inputs bad, but only some inputs, right? And so that's my next point, which is it's untargeted is more difficult to be detected. So with targeted, so you see that the model is performing well pretty much on all the stops, on all traffic signs, but only on the stop signs, it's weirdly underperforming, right? So in that case, it's easy to detect that there's a target. Because the goal of poisoning is to completely change the label of misclassification.
Untargeted, I guess you can just try to identify the separate within.
But in targeted, I guess my point is, again, it all very well depends on the application. But in many untargeted potential scenarios, you can think of the attacker, the hurt to performance, the reduction in accuracy, it doesn't have to be even significant. Again, it's all a matter of like 1 or 2 percentages, right? So like, think of like, I don't know, Microsoft and Google competing on like search results, right? So the dream of Microsoft, Apple's, Google's, I don't know, search engine's accuracy by only 1%. Even that is enough. And if it's done untargeted and uniformly across all input classes, then it's much more difficult to detect because maybe our algorithm is not good enough, right? Because it's underperforming on all the inputs. We only achieve a 94 accuracy compared to Microsoft 95 or 96. So it's easier, it's more difficult to detect because the harm could be very minimal, but it's still impactful because it's on all the input classes. In the case of targeted, I mean, the goal, again, depending on the application, but the goal is to misclassify or mislabel a stop sign as a green light. And now it's probably easier to detect because you see that only for some input classes, there's a different behavior in their perform. You go into checking or even fine tuning that single class of data. But again, so this discussion variable depends on the application, but at least my hypothesis is that untargeted is more critical for production FL because it's more difficult to detect. And the other thing is, which makes it more exciting for research, is that it's also more difficult to do untargeted poisoning. So with backdoors, there's a lot of backdoors. They perform very good performances. But then, and the reason is they only need to manipulate over a small space of gradients, right? Therefore, same with targeted attacks, right? So you only need to manipulate for some kind of input samples. But if you want to reduce the performance on all input classes, then you need to do more work. So these are, and in fact, I don't have results to compare targeted versus untargeted, but state-of-the-art performance on untargeted is significantly lower than targeted attacks. So there are much more efficient targeted and backdoor attacks that exist compared to untargeted attacks. And in fact, what I wanted to claim from, like, this is another paper, but another recent draft, what I wanted to claim is that at this time, we don't have any efficient untargeted attacks for production FL, because for realistic parameters of settings, in fact, whatever exists, whatever we know as untargeted poisoning attacks, all of them are not good enough. They're not a real threat, right? But on the other hand, whatever exists on untargeted attacks, targeted attacks and backdoors, they're very efficient, even with realistic scenarios and kind of assumptions. Okay, so let me, I guess I'll just move on perhaps to the last slide. I'll skip things. So I guess my summary slide is that I hope I was able to convince that poisoning is a potential major challenge to the widest scale adoption of federated learning. So people have been working on designing aggregation rules or defenses against poisoning, but there's a lot of challenges in applying them to production systems because I think, like, there was also some questions. There are heterogeneity in data of devices. There's constraints on the communication efficiency and also the computation resources of different devices and many other practical issues. And so we only talked about security or one particular type of security, which is poisoning attack, but there are other related issues to federated learning, in particular privacy and fairness. And there's often a challenging trade-off between these different features. So like if you try to improve security, it's likely that now your model is more vulnerable to privacy. I mean, not in all cases, but it's possible. So there's different other things many other things to think about when we think about a scalable and practical federated learning systems. And I guess that's all. This is just a slide of papers. And I guess at this time, if there's time left, and take more questions. If not, thank you. Mhm, mhm. So with data poisoning, well, I mean, still there could be a difference because let's say you find that the most malicious ranking is this particular ranking. Right? So with model poisoning, you can just submit that ranking to the server, right? But if you want to achieve that ranking with your data samples, it may or may not be possible depending on what data samples you have, right? Because again, you need to provide your model with some data samples that for those data samples, the best is your most malicious ranking, right? And again, it may be possible, but I mean, same as regular federated learning, you need to, I mean, it may not be possible. Or like finding the right data samples could be challenging. It may not be an easy task, right? And with model poisoning, you just submit whatever ranking you feel it's the most malicious. But with data, now you need to find, and also the other problem is, for a lot of users, this is when you submit or when you trick them to download some malicious data samples, it's also going to be aggregated or combined with other data samples that are benign. And therefore, the training also is impacted by the non-malicious data samples, right? So that could be the other challenge. Right?
So can I have a question?
Hold on, there's one question here and then I'll get to you.
Oh, sorry.
Oh, cool. Cool, cool. I'll make sure to check that out. Yeah.
Yeah, sure. We can talk about this.
Okay, okay. Thank you. Yeah, so I can take your question.
Yeah, so you mentioned about the poisoning attack in the federated learning. I have a question about the like the algorithm of the federated learning you consider about, because I think if you share the gradient and you share the weights, they are like different, like two kind of a different situation. But I suppose like what you described before is assuming that the federated learning is share the gradients, right? So they only aggregate the gradient in the centralized server.
Right.
But if they share the weights to the centralized server instead of the gradient, so is this kind of poisoning attack still like?
It has the same impact because I guess if I'm correctly understanding your question, you're asking whether it makes a difference. So like in federated learning, I mentioned like in vanilla federated learning, clients send updates. Alternatively, they can just send their new like model, right? So like when you fine tune, you can either send the diff, the delta of gradients, or you can send the new parameters, right?
Mm-hmm.
And it's so like they're both, and I think the question is whether one of them is more vulnerable or less vulnerable to poisoning. I think the answer is they're kind of the same because it doesn't matter if you're sending the model updates or the actual parameters. In both cases, I mean, even if you send the differences, then you can use them to reconstruct the model update in the client. So I think that both approaches are basically the same thing. There's no difference between them. I hope that was your question. I don't know, maybe.
What I'm confusing is like, so you say like in your kind of a poisoning attack, the key idea is to find the maximum distance between the benign aggregates and the malicious kind of updates, right? So that's one of my questions. So it's like, how can you find, let's say if we share the weight, how can you find the maximum distance if you not sharing with the gradients?
Oh, so I mean, so one thing to note is that the gradients are, I mean, are not necessarily available to the adversary, right? So like to do that attack, the adversary needs to obtain some ground truth data samples for benign samples, and this is locally assuming that this is the kind of the benign aggregate from the benign clients, right? So only the servers see actual benign updates. And therefore, it's the same thing. Like the attack is performed locally. So you just like the attacker has a sample data set of potential benign updates or benign data samples, and based on that, tries to solve that optimization problem locally. And again, depending on how good is your reference data sample of benign data, the performance of the attack would also be like depending on that.
Okay, I see. And all of the experiments is on the IID data set, right? IID data.
No, not really. I think in most of our own experiments there are non-IID. I think I didn't get to talk much about results, but like all of these are on non-IID. I think maybe I can go to yeah. So these are the data sets we're using, but then we're using a we distribute them between clients in a non-IID fashion.
Okay. Okay. Thank you.
Sure.
Okay.
All right.
Thank you very much.
Okay. Thanks everyone. Yeah. Thank you.